Our next speaker is Simon Shepard, and he's giving one of the first science highlights. It's entitled Large-Scale View of Mid-Latitude Plasma Convection.
All right, good morning, thank you. So as Rich just said, the superdarn radars are expanding everywhere, and I'll talk a little bit about some of that expansion. Talk about plasma flow from these radars at mid-latitudes. Here are some of the people involved in this expansion of the radars, and this doesn't include most of the students who probably do a lot of the work. So here's sort of a traditional view. I've been showing a slide similar to this for probably close to a decade. So you're looking at the northern hemisphere, and you'll see 9 radars, the field of views of these 9 radars, located roughly at 60 degrees geomagnetic latitude. So these are the high latitude superdarn radars that measure plasma convection in the Earth's polar region at F region altitudes. And so there's this line here. This is about 62 degrees geomagnetic latitude, and pretty much the network here sees measurements above this geomagnetic latitude. So here's part of the recent expansion. So this is a current view. So we've begun to expand equatorward, in part with help from the National Science Foundation. 2 radars were built at around 50 degrees geomagnetic here in Virginia at Wallops and Blackstone. Our Japanese colleagues built a radar in Hokkaido. And then as part of this project, we built 2 pairs of radars at 50 degrees in Kansas and Oregon. And so now our field of view is extended down to roughly 50 degrees geomagnetic latitude, okay? And for completeness here, there's our Canadian colleagues built 2 radars which are known as the polar darn radars up at about 70 degrees geomagnetic latitude. And so now we have this multi-layered view of the polar ionosphere, at least in the northern hemisphere. We also have radars in the southern hemisphere, but I'll focus on the northern hemisphere here. And so here are these sort of concentric rings in geomagnetic latitude of the regions at which these radars make measurements. So if you take a quick look, and so this is, if you take all the data from the 2011 from these radars and you organize it into those layers, the mid-latitude radars you see, so this is magnetic latitude, and this is just the number of data counts that you get. So the mid-latitude radars basically make observations from 50 degrees and above. Here you see they peak at around 60 degrees geomagnetic latitude. The high-latitude radars start making observations about 60 degrees, 62 degrees, and they peak around 70 degrees. And then the polar darn radars make their observations up above 75 degrees. So we have these 3 layers of complementary radars now where we have a complete view of the northern hemisphere. So I'm going to focus on observations from these 6 radars here located across North America here. And these are 4 of these radars, the ones in Oregon here and the ones in Kansas here, are part of this NSF-funded initiative, the MSI MSI project here that these 4 institutions are participating in. So just to show you quickly, without going into too much detail, so with these new radars, we're actually building 2 radars at a single site. And so combined, again, here's one radar that's looking in sort of the northwest direction. This is a view from Oregon, aerial view of the recently constructed radars there. And this radar here looks off in the northeasterly direction, and together they give you about 150 degrees field of view from a single site. And so there's a similar setup in Kansas to this. Okay, so what do these radars actually see? So here we're looking at a 1-minute time period from last month. So this is May 13th at 7 UT from this year. And what you're looking at here is just the observations, the line of sight observations from the 2 Christmas Valley radars. And what you see is the color here indicates the velocity, the line of sight velocity is measured by these 2 radars in the F region. And the scale here is, the upper scale here is 500 meters per second. And so the blue indicates motion towards the radar, the red indicates motion away from the radar. And so what you actually see here, sorry, this is the dawn-dusk, the terminator, nighttime terminator here. And so you see that these measurements are in the pre-midnight sector here from Christmas Valley. So what you see here is this relatively 5 degrees wide region of plasma drift that's moving in a westward direction here. And so if you look at beams that are more poleward here, you'll see that the flow in this region is very, the colors are darker and the flow is weak. The further away you go from this meridian direction, more zonally you look, the larger the velocities to get, indicating that this is westward flow across this extended region right here. And so this is the subaurora polarization stream as defined by or described by Foster and Burke recently. And it's a general feature that we see in these radars quite consistently. So you'll notice that this is, again, sorry, these green lines here are actually lines of geomagnetic latitude. So the plot here is in geographic coordinates, but the lines here are constant geomagnetic latitude. And you'll see in the middle of this particular feature a narrower feature that's about 2 degrees wide, which much higher velocities, and this is around 60 degrees geomagnetic latitude. And so if we move over to the Kansas radars, there's a pair of radars that were built in 2009. You'll see a similar feature here, again, of westward flow. We move over to the two Virginia radars, and you'll notice that we still see this same feature right here. This, by the way, is ground scatter. It's a different type of scatter that doesn't come from the ionosphere. And so that's not, I'm talking about this particular form of scatter, backscatter right here. And so if I flip back here, you'll notice that as you move westward here, the velocity increases, okay? So as I move eastward, we still see this persistent feature here at subaurora latitudes, but the velocity here decreases, okay? And this is a repeatable feature. So if we look at all of them here, this is the overlaid. It gets a little bit messy here, but you'll see that the observations from these 6 radars are consistent, and right around 60 degrees here, you'll see this fairly narrow channel of westward drift, okay? This is the subauroral polarization stream. So this is a feature that's been well studied, and it tends to occur in regions of low plasma density associated with pressure gradients in the inner magnetosphere. And so I'm simply showing you right here, so this is a plot from the Virginia Tech website here. So this is TEC in color here. And notice I've cranked the scale down here, so the maximum here is 8. And so you see this region of very low plasma density right here. And right here is the backscatter power from all of those 6 radars across the U.S. So you'll notice that occurs right at the poleward edge of that density trough right here. Just a little bit about what's going on at this time. So it turns out that we observed this feature. That was a 1-minute snapshot, and we observed this particular feature on this day for over 2 hours of universal time. So I'm showing you data from 3 different days here, and the yellow band here is the 2 hours at which we make these observations. And so there's nothing spectacular about this particular event. IMF was southward here. It was roughly -4 nanotesla, somewhat variable. SIM-H here was maybe -30. It looked like in perhaps a recovery phase, but things were quite variable here. And KP was 3 and decreasing, okay? So sort of moderate activity. So if you look, and I'm just looking at those 2 hours now of time from the Christmas Valley radars, it gets a little messy if you look at the line of sights all over the top of each other. But you notice this feature extends from the early morning as the Earth rotates around all the way over to close to dawn over here. Okay, sorry, early evening over here. And this feature is persistent, but there's velocity variations in here, and we'll look at those in a little bit more detail. So the way we do that, again, if I plot all these over each other, it gets quite messy here. So our standard analysis here is we put things onto an equal area grid, and this is just indicating a 1 degree latitude equal area grid. So now we take all these line of sight measurements and we put them into this framework in geomagnetic coordinates here. And these data points here are then the line of sight velocities on that particular grid. And in certain regions, particularly here between the Christmas Valley, the eastward-looking Christmas Valley radar, the westward-looking Kansas radar, you see that there's overlap of these field of views. The same is true for the Blackstone radar and the Fort Hays East radar. And so in those particular regions, right, we have line-of-sight velocities from two different directions, and we can actually reconstruct the two-dimensional velocity flow. And so that's what you're seeing right here in these pink vectors, okay? So here's a little bit clearer, our takeaway. Now we're looking in MLT coordinates here. So this is midnight, and this is magnetic latitude from 50 degrees up to the pole here. So again, you're looking, these are line of sight velocities here. You notice that the length of these and the color is bright over here, indicating stronger flows. The further west you go into the pre-midnight sector here, and they're less in the dawn as you get closer and closer to dawn. So in these two regions here, over about 4 hours of magnetic local time, we actually can make measurements of the two-dimensional velocity flow in this particular feature. So if you look at this, again, you'll notice that, again, these are the reconstructed two-dimensional velocities, velocity vectors from those overlapping field of views from those 6 radars in the northern hemisphere. And this is just a 2 hours from 6 to 8 MLT, and it covers up to 6 hours of MLT, okay? Particularly if you include the line of sight velocities in here. So if you look at this, the velocity variation, as you sort of noticed as you watch this in time, and both in MLT is quite variable. So to look at that a little bit, I look at 10-minute segments here. And so this is a 10-minute segment early on in the period where I'm simply plotting versus MLT now. These are the pink vectors, and so these are the merged vectors, or the two-dimensional velocity flow that you see. And on this axis in meters per second is the strength of the flow. And so you can see there's quite a bit of variation in MLT, in the velocities, even in these two-dimensional flows for that particular period early on in this particular period. As we go to later in the period, this is towards the end of this particular event, we see that the flow, actually the variation is more linear in this particular instance. If you look at the azimuthal angle, so this is the direction relative to the north geomagnetic pole of these particular velocity vectors. This is simply a histogram. This minus 90 is then westward flow. And then these velocities here are certainly, there were a few velocities, if you look there, were from higher latitudes. This is the eastward flow up at higher geomagnetic latitudes. So most of this flow is directed in a westward direction. These are only the two-dimensional velocity vectors that I'm plotting right here. So if you look at this peak, you fit a Gaussian to this peak, it's about minus 83 degrees plus or minus 7 degrees. So there's some azimuthal variation, but it's strongly directed in the westward direction. So if we take that, the reason I'm actually looking at that is because if you go back, there's only about 4 hours of magnetic local time where we actually have overlap of the, and can make these two-dimensional velocity vectors. But there's a much wider extended region where we actually have line of sight measurements. And so if we extend that region by using the direction determined from the merged vectors, and then we project those and use those as the inferred velocities of this particular feature here, then you see that we can extend our observations from I mean, this is 7 hours of MLT that we actually see now. Okay. It's a little bit easier, I think, to see if you plot this in this fashion. So again, this is MLT from 18, so this is dusk and this is dawn over here. And now I'm only looking at 50 degrees up to 70 degrees geomagnetic latitude. And you'll see this, so you see this is the several degree wide, 5 degree wide SAPS feature right here with stronger velocities in the middle. The velocities are stronger in pre-midnight than they are in post-midnight, and you'll see that the that this feature is located above 60 degrees in the pre-midnight sector and below 60 degrees in the post-midnight sector. And so if we just simply watch this again, you can see that the two-dimensional velocity vectors, you see that here is the 83 degrees, so there's a poleward component of the velocity in the pre-midnight sector. And if you watch this carefully, you see there's a southward or equatorward directed flow in the post-midnight sector. Okay, so if we take those velocities then, and we include those projected or inferred vectors in this plot here of velocity for these 10 minutes here, then you can see, so these are the velocities from the Christmas Valley West radar, which currently have no pair to make these two-dimensional velocity flows. You see that there's sort of an exponent, at least early in this period, there's an exponential dependence of the velocity on magnetic local time. And this has been reported before in a different case study. But if you go later in the period here, then you'll see more of a linear trend, and I discount this particular data point right here. This is almost certainly from a beam that's looking almost perpendicular to the flow direction, and small variations in that will give you large velocities here. So you can see that later in the period that this is quite a linear flow here. So just to summarize this particular event, so this is one event. We see these all the time when KP is above 2 to 3 and above with these mid-latitude radars. So this is a subaurora polarization stream. We're looking at, we can now resolve two-dimensional velocity vectors at 1 minute time resolution. And those two-dimensional velocity vectors extend over about 5 hours of MLT. If you include those line-of-sight velocities, we can go up to greater than 7 hours. The peak flows are near 60 degrees. Again, they've above 60 degrees in the pre-midnight sector and below 60 degrees in the post-midnight sector. The peak flows are a few degrees wide, up to 3 degrees wide, westward flow directed. For the two-dimensional velocity vectors, we see kilometer a second flows, and then if you include those inferred velocity vectors, discounting those anomalies, you get velocities up to about 2 kilometers a second. So these are some other recent studies that have used a similar technique to use mostly studying these inferred velocity vectors. So Lasse Clausen looked at a similar earlier event using this particular type of analysis and came up with similar results here. Using Millstone Hill data in a statistical sense, this large database of Millstone Hill data, Foster and Vo, and also Phil Erickson et al. Came up with similar results to this in a statistical sense to these observations here. I still have a question as to whether the MLT dependence of the velocity is linear or exponential, and I think we see both. So I'm not sure that question is actually answered. So how does this impact the large-scale convection? So on the right now, you're looking at 12 MLT. So this is dawn, dusk here. You're looking down on the northern hemisphere. And this is our standard convection mapping technique where we take the line-of-sight velocities from all the SuperDARN radars and we fit it to an expansion of spherical harmonics. And you're looking now at the standard two-cell convection pattern for, in this case, it's a 2-minute period somewhere in the middle of this particular event. And this is only the high-latitude radars. So those are those 9 radars that you saw in that first slide. So if we include all of the radars, the polar DARN radars and the now 7 mid-latitude radars, well then you see that the flows, there's a strong component of westward flow that's completely missing because it's out of the field of view of those particular radars. And this gives you, 2 minutes, thank you. And this gives you a very distorted dusk cell that we see repeatedly in the observations when we include the mid-latitude radars, which make measurements down below this 60-degree cutoff. So in the last minute, I'm just going to run through this quickly here so we can look at this statistically. And I've taken all the data from 3 years of the SuperDARN radars, and I'm looking at a comparison between high latitude only and all radars. And so what I've done is I've taken all the measurements for those 3 years and I've been by KP. Okay, just binning by KP, no IMF, and I throw them all into a fitting technique here, and I come up with this. This is the average pattern for KP of 1 for those 3 years. Okay, only using the high latitude radars. And here's all the radars. And so you can see that there's stronger flows, westward directed flows, even at KP of 1 when we include those mid-latitude radars. As the activity increases, KP of 2 in this particular case, you can see the convection region expanding, flows increasing, and you can see the impact of these mid-latitude radars is getting more important and more important in this particular region. At KP of 3 here, you can see that the large flows right up against the edge of the field of view of those high latitude radars, and so we're starting to miss some of the convection that you would see when you look at the include the mid-latitude radars, and this simply continues as you go KP of 4, KP of 5, etc. Okay, and last couple slides here. If you look at the cross-polar cap potential, this is only for the high latitudes. This is versus KP here. You see again at about KP of 3, this is why I've used these open circles here, things start to trail off. Okay. If you include all of the radars now down to the mid-latitudes, you get a nice linear dependence here, roughly linear dependence with KP on the cross-polar cap potential. Again, this is the average convection, not taking into account any IMF or anything else. Okay, so summary, mid-latitude, we've made, we're extending, as Rich said, these radars are everywhere now. We're extending poleward, we're extending to mid-latitudes. And so we now can make observations 50 degrees and below for 7 hours of MLT. This is soon to be 12. We regularly observe this SAPS for KP of greater than or equal to 2. And we can now continuously measure the two-dimensional flows for up to 5 hours of MLT. So the impact is a distorted night-side convection for KP as low as 1, strong westward flows at low latitude, and there's an increased transpolar potential, of course, and that effect increases with KP. I didn't mention anything about it, but there's also other types of backscatter that we observe during quiet periods. And this is also work that's ongoing. And I'll simply leave you with this particular slide. So this year, we plan to actually add 4 new radars to this particular network. Bill Bristow at University of Alaska Fairbanks is leading an effort to build 2 radars in ADAC. And then we're in the process of negotiating contracts to build 2 radars in the Azores, so eventually we can extend the MLT coverage of these two-dimensional flows. Thank you.